Hello, everyone. Thank you for tuning into my talk. My name is Charlie Young, and today I'd like to show you some work I've been doing in Charles Singh's group at the University of Illinois in collaboration with Charles Schroeder's group on the dynamics of semi-dilute solutions of ring linear polymer blends in planar extensional flow. Our motivation for studying this topic is that polymer solution dynamics are generally relevant to a wide range of processing applications. Some common examples are drop casting, spin coating, and 3D printing. On the right, I'm showing a couple examples of research being done at the University of Illinois in which polymer architectures are actually being used in targeted applications to achieve kind of specific material properties. In the middle, this is work from Nancy So's and Jeff Moore's group in which they are using a cyclic polymer topology in order to have a controlled depolymerization and repolymerization cycle for recyclable plastics. And they have shown that these polymers are highly reproducible over multiple generations without any degradation of the mechanical properties. On the right, I'm showing some work from Professor Ying Diao's group in which she uses comb polymers in solution printing of organic thin film transistors. In this case, the side chain branches increase the solubility of the comb and result in increased alignment and uniformity of the film after printing. The interest of our research is to understand really the fundamental conformational dynamics of these polymers and flows, because that really determines the solution rheology, determines how these polymers should be processed, and often there's a close relationship between the conformational dynamics in flows and the resulting material properties of the final product. So focusing in on ring polymers here, there's a wide variety of variables to tune, but three that we're interested in particular are the flow rate, the polymer concentration, and the blend ratio. The flow rate I will refer to as the Weissenberg number, so the strain rate made dimensionless by the longest polymer relaxation time. The polymer concentration, here we have our standard C star overlap concentration, entanglement concentration, and melt concentration. And finally, the blend ratio is just the mass fraction ratio of ring polymers to linear polymers in the solution. So I'm not going to go over each of these examples specifically. I'm just noting here that there's been a lot of interest in this area of research in recent years. But one specific gap is in the semi-dilute non-equilibrium regime. There's really primarily one study here that's been done by our collaborators, Peter Zhu and Charles Schroeder, on ring polymers, trace ring polymers in a semi-dilute linear background at the overlap concentration for varying Weissenberg number in planar extensional flow. Now, the goal of this project is to extend that out to varying blend ratios and also to use molecular simulations to try and understand what is the kind of the driving force for ring dynamics there. This is just some more details of the experimental and simulation methodology. On the left, I have the experiments and also a movie here that Peter's taken. So the general scheme here is that he flows in a semi-dilute solution blend of ring and linear polymers into a cross-slot microfluidic device, which induces an extensional flow upon the polymers that stretches them here along the x-axis. So this is done with 48 kbp DNA, about 200 Kuhn steps at the overlap concentration C star. And they fluorescently label a trace amount of ring polymers for imaging by confocal fluorescence microscopy. And then they use a Stokes trap device to trap the ring polymer that's tagged at the stagnation point for long time duration viewing upon flow application. Now, on the right, I'm showing here the Brownian dynamics simulation method and then also a simulation movie. So here, the equation of motion of the polymer is given by the applied solvent deformation, so planar extensional flow. Then we have our pairwise potential. So here we're using a Kramer-Gress model with a Feeney spring and WECA excluded volume that models the polymer at about 1 Kuhn step per spring and enforces entanglement constraints. This is a Brownian dynamics implicit model, so we need to put in our hydrodynamic interactions via our RPY tensor. And then the final ingredient here is the Brownian noise, or the thermal fluctuations. And I won't go too much into the details of how we calculate this. I'll just mention that we are using an iterative conformational averaging method that we've developed in the SING group over the last few years to significantly speed up this calculation, which is normally the bottleneck in BD simulations. And if you're, so that allows us to kind of reach the relevant time and length scale seen in the experiment. And if you're interested in more details on how that's done, I would refer you to these papers. Before I jump into the ring linear blend results, I'm going to cover some background on pure linear polymer solutions. So these are results from a study done in Charles Schroeder's group back in 2016, where they apply the planar extensional flow to a pure linear polymer solution and they vary the Weissenberg number and the concentration. And the key result here is that the steady state fractional extension, which is the stretch of the polymer in the flow direction normalized by the contour length, that at some point at a Weissenberg number of about 1, when the inverse strain rate exceeds the longest polymer relaxation time, the polymer is unable to relax its stress, so it stretches out from the equilibrium random walk coil state to being stretched and aligned in the flow direction. This is qualitatively consistent for all the concentrations they investigated from the dilute limit up to C star. So this is the steady state behavior. And then if we look at the transient behavior for a specific concentration at Weissenberg number, we see that, again, the polymers starting from their equilibrium random walk state stretch out and align in the flow direction. So these are experiments up on top, and down below we have the simulation results from BD 1C star simulations that I've done, which show qualitatively consistent results that the polymers just stretch out and remain stretched for the duration of the applied flow. Now getting into the ring linear blend results, we again have the experimental results here on top and the simulation results on the bottom for the transient fractional extension trajectories. And in the kind of majority ring polymer blend case, so here this is an 83% rings and 17% linear polymers at the overlap concentration C star. There are qualitatively consistent dynamics of the rings as compared to the pure linear polymer solutions, where the rings just stretch and align in the flow direction and then remain stretched. And really the unique and interesting dynamics here occur as we vary the blend ratio. So over here I'm showing a trace ring polymer in a linear background at the same total polymer concentration. And in this case, we observe transient fractional extension overshoots upon the startup of flow. And at steady state, we have these large conformational fluctuations between coiled and stretched states. So these are, fairly unique to these ring polymers, or at least they haven't been seen in the pure linear polymer solutions. And both effects are fairly sensitive to the blend ratio. Here I'm showing the average conformational fluctuations, so the root mean squared average over time, and the ensemble size as a function of the Weissenberg number and the blend ratio. Starting with the kind of canonical case of a pure linear polymer solution, we see the expected results of a peaked fluctuations at Weissenberg number 0.5, the critical coil stretch transition rate where the polymers are fluctuating between coiled and stretched, and then decreasing fluctuations for higher Weissenberg numbers as the polymers become stretched and aligned. And in the pure ring polymer solution case, again, qualitatively consistent results. The conformational fluctuations are lower just because of the closed loop constraint. But really the interesting result here is that as we vary the blend composition from the pure ring case to a trace ring case in a linear background, these fluctuations are growing and they're no longer peaked at Weissenberg number 0.5. They're peaked at around 1.5 or 2, and then they're plateauing out for a high Weissenberg number. And these fluctuations are growing as we vary the blend ratio towards a linear polymer solution. I'll also just note here, interestingly, that when we perform these same simulations without hydrodynamics, so still semi-dilute, the fluctuations are much lower and they actually about collapse with the dilute solution case. These are the results from the simulation on the left, and on the right I'm showing the results from the experiment, which are qualitatively consistent to within the error bars of the experiment and the kind of coarse graining errors of the simulation. So we say here that we have some qualitatively consistent results that both the experiments and the simulations show these large conformational fluctuations of ring polymers in a linear polymer blend. Now I'm going to move into some detailed analysis of the molecular simulation trajectories to try and explain some of these unique dynamics we observe. So starting with the transient extension overshoots upon startup of flow, we see that generally these are driven by advection of folded or coiled linear polymers into the surface of the ring, such that they form these strong topological intermolecular hookings that significantly deform the ring. And the ring, because it has the closed loop constraint, it's not able to relax that hook easily as two linear polymers would. So that drives the overshoot in ring polymer extension until the linear polymer is fully stretched and aligned, and then the hook can be released and the ring can retract. I'm also showing here on the right an example of ring-ring hooking, which is qualitatively similar. This is much more rare. Mostly we see the extension overshoots are driven by the ring linear hooks. I'm just showing the ring-ring case for demonstrative purposes to show that this is also observed in our simulation, and this could be relevant at higher concentrations than in melts. We can go ahead and quantify how often these hooks occur upon startup of flow. I am not showing any of the details here, but there are more details in the paper we've just posted if you're interested in seeing. And the key result here is that as we vary the blend ratio from a pure ring polymer solution to a trace ring in a linear background, we see more and more of these ring linear hooks, which is as you would expect. When there's more linear polymers, there's more opportunities to form the hooks. And importantly, they occur much more often than in the pure linear polymer solution case. So we can also have qualitatively similar linear polymer hooks, but they occur much less often than in the ring case because the ring has the closed loop constraint. Now, importantly, these kind of conformational these kind of intermolecular topological constraints don't actually explain the steady state fluctuations that we observe in the simulations. We find actually that those fluctuations are driven by intermolecular hydrodynamic interactions. Here I've highlighted two examples of a highly stretched ring polymer and a retracting and tumbling ring polymer. And I've co-plotted the conformation of the ring polymer with the streamlines, which are due to the applied planar extensional flow, plus the disturbance velocity due to the surrounding ring and linear polymers. And generally what we see is that the linear polymers, according to their concentration gradients in space surrounding the ring polymer, can either induce these really strong extensional flows, so much stronger than the underlying planar extension, which highly stretch the ring, or they can conversely show these rotational flows. They can induce this vorticity, which causes the polymer to retract and tumble. So this is looking at the flow just surrounding a tagged ring polymer. We can also look at the bulk flow more generally, where here the key result is that for non-dilute polymer solutions at Weissenberg numbers greater than 1, the elastic stress that the polymers impose upon the solution tends to lead to these instabilities in the flow. So you get deviations away from the planar extension. So you get stagnation point displacement at moderate Weissenberg number, and then at higher Weissenberg number you get actual asymmetry and bifurcation across the axis of extension. And qualitatively, this is actually quite similar to what we see in experiment. We're still investigating some of the quantitative details of how these two compare, but we do see fairly similar results where we see these large spatio-temporal fluctuations in the flow, where you get these areas of shear and vorticity. And this is still something that we're evaluating, but we think that this could offer a really nice explanation as to why our ring polymer conformational fluctuations increase as you vary the blend towards being a pure linear polymer solution. The reason for that is that the linear polymers have a higher relaxation time. They have a larger contour length, so they're more stretched in the flow. They impose more stress, and they tend to lead to these instabilities at lower strain rate. So even though the Weissenberg number with respect to the ring relaxation time is low, the kind of background fluid relaxation, the background fluid Weissenberg number is quite high. So if we looked here at the flow profile for the same strain rate, but for a pure ring polymer solution, the flow would be much more stable. You wouldn't see these kind of shear and rotational regions that cause the ring fluctuations. We can also kind of look at more detail in really what is the role of polymer architecture here versus what is just due to the difference in size and length scales and time scales of our two polymers. So here we're considering a bidispersed linear polymer blend where we've matched the contour length of our short linear polymers to that of our rings. So you just imagine that you take all of your ring polymers and cut them in two places so that you get two equivalent short linear polymers. And then we keep everything else the same, the polymer concentration and the mass fraction, that's all the same. And what we observe in this case is that there are no longer the overshoots and extension upon startup of flow. That appears to be unique to the rings because they have the closed loop constraint, so they cannot relax the hook until the linear polymer becomes fully stretched. However, these steady state fluctuations are still present in this bidispersed linear blend case. So I'm just showing an example trajectory in a movie here. So this appears to be due to the the differences in length scales and time scales of the two components of your blend. We can again go ahead and quantify these fluctuations using our average fluctuation quantity. And here we see qualitatively consistent behavior between our two blends at the 50-50 mass fraction, where the short linear polymers with the matched contour length to the ring display the same trend in fluctuations with Weissenberg number, where it increases as opposed to being peaked at Weissenberg number 0.5. So just to summarize, we've observed some fairly unique dynamics in ring linear polymer blends in planar extensional flows, where there are these transient fractional extension overshoots on startup of flow due to these intermolecular hooking events. And at steady state, there are large conformational fluctuations due to intermolecular HI, which drive flow instability. I'll also just quickly note that we have extended our simulation method and our experimental synthesis to include comb polymers as well. So this is, these papers are in preparation and review, but if you're interested in combs, I'd encourage you to keep an eye out for them. So I'd like to thank my collaborators from the Schroeder group, as well as our funding sources and the other members of the SING group. And if you have any questions, I'd encourage you to join the Zoom call for the Section 8A Graduate Excellence in Polymers Research from 8 to 9 a.m. Pacific Standard Time. And then if you'd like to see more details that I haven't shown in this presentation, I've just linked to our archive paper that we just put up. That's on iPoster. Both of those links are on the iPoster. And finally, I'll just do some self-advertisement here and say that I'm planning to graduate in this upcoming semester, and I'll be searching for a postdoc in the area of complex fluids and non-Newtonian fluid mechanics. So if you are aware of any positions, feel free to contact me. Thanks for tuning in.